Okay, so now we can we start the second segment in module 2, where we will be continuing our discussion on random variables, and we will be looking at two important properties of expectation. One is the linearity of expectation, and the other is called the Jensen's inequality. Okay. Linearity of expectation, we will study it with so in studying that we will introduce this distribution called binomial distribution, again a very fundamental distribution, shows up heavily in computing, and we will introduce Jensen's inequality by trying to understand what the area of a square, random square is. So, let us start with the linearity of expectation. It is a very useful theorem, and let me state it. So, let us consider two random variables x and y, okay, and they have finite expectations. They do not need to be finite in the sample space, but their expectations must be finite, and a and b are some arbitrary constants. So, we are interested in what is the expectation. So, now when you think about it, this itself, this ax plus by itself is a random variable. You can take two random variables and you can add them, you can apply some functions on them, and outcome will again be a random variable. Why? Because it is just a composition of functions. Remember, x itself is a function, y itself is a function, you compose them and you get this new function on the sample space. It is a function on the sample space, and therefore, it is a random variable. Okay. So, this expectation E of ax plus by is a randam variable. So, you can ask what is the expectation of this random variable ax plus by, and as it turns out it equals a times E of x, the expectation of x, plus b times expectation of y. So, this is the most natural thing that you would suspect its value to be, and that is exactly what we get. Okay. What is surprising is that later on we will see other quantities, other notions, other ways to understand the random variable for which this will not hold unless you have other conditions like independence of random variables and things like that. So, here in this theorem, the important thing is there is no restriction. It is any two random variables x and y, you take expectation of ax plus by, you get a times E of x plus b times E of y. Okay. So, this is the linearity of expectation, and the proof is also quite simple. What is the expectation of ax plus by? Now, what you have to do is consider all possible values of x and y. So, possible values of x is lowercase x, possible values of y is lowercase y, and it is just the sum of the weighted sum of the those values, right. So, ax plus by weighted by the probabilities. Remember, a and b are constants, so they do not have probabilities associated with them, but we can take what is the probability that random variable x takes this little x, and the random variable y takes this little y. Okay. And you just sum up over all possible values that x and y can take, okay, and then we will play with the summation. Now, what we do, we arrange it so that what happens over here is we put the summation x first and the summation y first, and so basically what we do here is we take this probability term and multiply it by ax, then probability term multiplied by by. That is the two terms that we get, but then when we write it down, we put the in the first term we put the x coming first, so that what the advantage that this has is that this x should be inside over here, but it can come out of the y. Because summing over y, the x is going to stay common. So, you can bring it out, and a is going to be common throughout. It is not going to be affected by the values that x takes or the values that y takes. So, a comes out all the way outside the summation, x comes out, but it cannot come out of the summation of x, it can come out of the summation of y. And then you have the probability inside, because this probability is dependent on y as well. So, you cannot bring it out of this summation. So, that is the first term that you have over here, and then the second term similarly you treat it. The constant b comes out all the way. In the summation you put the y first and then the x comes. So, the y is able to come out of the inner summation, but it cannot come out of the outer summation. So, this is a very straightforward thing to do when you think about it. Now, what about this quantity? Okay. And you think about it, the x equal to x is one event, and you are summing that intersected with y equal to y for all possible values of y. What does that remind you of? It is the law of total probability. The y equal to y is going to range the entire sample space. So, what do you get out of this? This is nothing but the probability that x equal to x, and similarly you get probability that y equal to y over here. Okay. But of course, now what is this quantity? This is nothing but the definition of the expectation of x. Okay. So, that is what you get over here. Similarly, this is the definition of the expectation of y. You get a times expectation of x plus b times expectation of y, and that ends the proof of this theorem. So, we will try to now apply this theorem. So, very simple application, but nevertheless, please bear with me, because simplicity means it is important. Okay. And this is generally going to be true when things have a very simple, clear explanation. That means they will show up again and again and again. So, that means it is important. Okay. So, the binomial distribution is simply this. So, you consider n Bernoulli trials, each with bias p. When you say bias p, the success happens with probability p, or you can think of it as heads occurring with probability p. The number of heads obtained under this experiment represents the binomial distribution. So, you toss a coin n times, biased coin with probability p of heads, count the number of times the heads appears, that is the binomial distribution, and it is usually denoted b n comma p. The two parameters that define this distribution are the number of times you toss the coin n and the probability p. Okay. And when we think of a random variable x that has this binomial distribution, we denote it as x drawn from b and p. That is the notation we use, x tilde b and p. Okay. Let us get our feet wet. What is the probability that x equal to I? It is very easy to see how x, what are we asking? So, x can take the values either 0 when no heads appears, or n when all the tosses outcome are heads. We pick a particular value I and ask what is the probability that x can take that value I. So, let us focus on a particular situation where there is a set of locations, in particular I locations, where heads we want heads to occur, the rest of them tails. Okay. So, if you think about it, each location where we want the tails to occur, what we are expecting, what we want is an event with probability 1 minus p to occur, because we want tails to occur over there, and wherever we want heads to occur, that event will occur with probability p. Okay. So, we just pick some I locations for h, and we put probability p for all of them. The remaining ones will be 1 minus p. So, if you specify the locations for the heads, the outcome has the probability p raised to the I, and these are all independent tosses. So, you can multiply the probabilities, p raised to the I times 1 minus p raised to the n minus I for all the remaining locations. Okay. This probability works when you have specified the locations for the heads. Okay. But that obviously you cannot do, you do not know where the heads will occur. So, you will have to choose, you have to find out all the you have to consider all the n choose I possible ways in which the I heads can occur, right. That is n choose I mutually disjoint events. If it is mutually disjoint, you do not multiply, you add them up. So, and there are n choose I of them. So, you basically n choose I times p raised to the I times 1 minus p raised to the n minus I. Basically, you have taken p raised to the I and 1 minus p raised to n minus I, you have added it n choose I times. So, that is where the multiplication comes from. Okay. So, this is the probability that x equal to I. Now, let us look at computing the expectation of this random variable. So, by the formula we get this. So, you basically sum over all possible values of I, that is going to be I is the values that x can take. So, it can be 0 when no heads occurs, or n, so when all of them are heads, and you sum over all i's, but then weighted by their individual probabilities. and I do not know how to deal with this summation. I am sure there is some way you can get this to work, but it is a little bit messy. Okay. So, what saves the day for us is that we can apply linearity of expectation. So, there is a very simple way to compute the expectation of the binomial distribution, and what we do is we break down the binomial distribution into individual Bernoulli trials, and then we somehow rebuild using linearity of expectation. So, what we do, let us break it down first. There are n coin tosses. Okay. We use xi equal to 1, it is a new random variable that we are defining. In fact, we will define n such random variables. Xi will be equal to 1 if the ith toss is a 1, otherwise xi is 0. Okay. And we know E of xi is p. So, now we know that the number, the total number of heads that we are going to get is simply the summation of x1 plus x2 and so on up to xn. Basically, take each one of them. If you get a heads, it accounts towards this capital X, otherwise not. So, it is just a summation. So, clearly you can take expectation on both sides, where so E of x is equal to E of x1 plus x2 plus and so on up to xn. And so, now well, at this point we do not know what to do with the right hand side, but if you just apply linearity of expectation, immediately you know what to do with it. Each one of them, E of x1 is a p, E of x2 is a p, and E of xn is a p. There are n such terms. So, the total expectation is n times p. That is linearity of expectation for you. It is very powerful, very simple, and very useful for us. Okay. In the same context of random variables, let us look at Jensen's inequality. So, let us motivate that by a simple example. Suppose you consider a random square, and what do I mean by that? So, the edge length x is chosen uniformly at random from the range 1 to 99. So, let us say it is an integer value. So, questions that we can ask, what is the expected value of its area? So, you take x squared, and you ask what is the expectation of x squared. And one question that should come to mind is E of x squared the same as E of x the whole squared? And in this context, we are going to just see how these two relate to each other. So, let us for that let us think, notice that this x squared is a convex function. So, let us just be precise about what we mean by a convex function. So, here is the definition. So, there is a way of defining it as 3 equivalent statements. So, f is convex, and then the 3 other 2 statements, equivalent statements that define the notion of convexity is the following. So, suppose you have, so we have shown this function f over here, right. So, it is just this curve shown over here. It is convex if for any 2 points, say x1 and x2 that you choose, you look at some intermediate point, and that is defined by this parameter lambda. So, when you take lambda times x1 plus 1 minus lambda times x2, you get a point somewhere in the middle. So, that is shown in this blue. That is the blue expression here, lambda x1 plus 1 minus lambda x2. Now, if you take you apply f for that function, that is the left hand side. And the claim is for a convex function, what happens when you take the f, you get to this point on the function, that is this purple point over here. You compare that with the point. So, now if you think of f of x1, that is f of x1 over here, f of x2 is over here, and then you take the corresponding point parameterized by lambda in the between the segment in the segment connecting f of x1 to f of x2. Now, the comparison of these 2 points gives you a definition of whether the curve is convex or not. For convexity, what you need is that this point on the curve should be less than or equal to this intermediate point by just joining those 2 points f of x1 and f of x2 by a line segment. So, and that should be true for any choice of x1 and any choice of lambda. Okay. And many of these functions that all of these x squared, x to the 4 and all are going to be convex functions. Another way to think about it is if you take the second derivative, and if the second derivative is non-negative, then again you can say that the function is convex. Okay. So, what does Jensen's inequality say? If f is a convex function, then the expectation of f of x is at least f of the expectation of x. Okay. So, this is a quite fundamental inequality that you shows up every once in a while. Okay. And so, let us quickly look at the proof. In the proof, we are going to do the simple version where there is a Taylor expansion for this function. The proof holds more generally, just to be clear, and you can actually try it out, try proving it more generally. There is an exercise in the textbook which gives you a hint to prove it more generally as well. But for our purposes, we will just quickly prove it under the assumption that there is a Taylor's expansion. So, another standard notation, expectation of x is often denoted as just mu, okay, when the context is clear. Okay. So, I am just going to use mu to represent expectation of x, and remember mu is just essentially a scalar value. So, f of x can be written as f of mu plus f dash of mu times x minus mu plus f second derivative of f applied at mu times x minus mu squared over 2. This is based on standard Taylor note. You take the Taylor series and just capture the first two terms as is, but then the rest of the terms are captured by this third term over here. The nice thing you have is, recall that the convexity gives you that f the second derivative is always going to be greater than or equal to 0. So, this third term over here is going to be a positive term, or at least a non-negative term. So, what do? We simply get rid of the third term and replace the equality by a inequality. So, now we apply expectation on both sides. So, basically we have f of x is greater than or equal to f of mu plus and so on. We just apply expectation on both sides. On the right hand side, you have expectation over a larger term, I mean summation of two terms. You apply linearity of expectation. So far we are doing things that are quite straightforward. Now here what are we doing? This f prime of mu is just a scalar value. Okay. Remember e times a of x is a times e of x, we have already seen that. So, we simply get the scalar value out over here. So, it is just f prime of mu become times e of x and e of x minus e of mu. Expectation of a constant is just a constant itself. Okay. E of x is anyway just mu, and then there is this f prime of mu. Okay. And here what are we doing? We are taking expectation of f of mu is again just f of mu, because f of mu is just a constant or scalar value, but mu is essentially e of x. And here you of course have this mu minus mu. So, this term cancels out, you are left with f of e of x. So, this establishes the Jensen's inequality. Okay. Just going back to the example, if you apply this, what you will get is, well, what is e of x? E of x is going to be 50. Okay, x ranges from 1 to 99, right. So, the e of x is going to be 50. 50 squared is something like some 2500, but e of x squared, if you work it out, is going to be a larger quantity. So, that is just an example where it works out that way. The important thing to keep in mind is that we are actually, what we are doing is we are working our way towards understanding of some other measures. So, for example, this if you notice that e of x squared is larger than e of x the whole squared, the difference, as it turns out, is actually an important measure. It tells you how much a random variable tends to deviate from its mean value, from its expected value. Okay. So, that itself is an important measure. So, with that we end this segment where we studied the expected value of a random variable and just proved something called the proved the linearity of expectation and now the Jensen's inequality. And so, with that we'll have to get ready for conditional expectation, which is some more understanding of how expectation works. Okay.